Okay, so today is a day where we are going to hopefully understand really the shape of the CMB power spectrum CL. So the image on this screen will come in very soon. Yeah, here it is. I will do a bit of fine tuning in order to get space also on the blackboard, like this. Okay. So we found that there is a fantastic quantity, the CLs, which can be both predicted by the theory and measured by observer. It's a variance of our ALM coefficient of the temperature anisotropy map, and it's given by an integral over Fourier mode of the primordial spectrum multiplied by this multiple L of the transfer function of neutrino temperature anisotropies at time eta 0. So if we want to compute the CL, we need to understand the shape of this function. And for that, we will rely on the implicit solution found by Zaldariaga, which is an integral over times, which is why people call it the line of sight integral, with these three terms. And you remember, in each term, you get a function telling you when the effect is important. Then the transfer function of the quantities that really produce the photon anisotropies. And then this projection kernel, which projects a Fourier mode of wave number k living at time eta onto an observable multiple L. And so in summary, what we need to understand if we want to get to the CLs are exactly four transfer functions. The monopole of the temperature fluctuation anisotropy, the gravitational potential and the other metric perturbation, phi m psi, and theta b, which is the divergence of the bulk velocity of the photon. So this is our program to try to understand these quantities. The most important actually is theta 0. Everything follows from theta 0. And so we derived an approximate equation for theta 0. The exact equation would be the Boltzmann hierarchy. It's a bit too complicated. So we are working now in the tight coupling approximation, which is a good approximation before decoupling, for which we have a closed equation for theta 0, which has a structure of a driven harmonic oscillator with a time-dependent mass. So here we have the pressure force, here we have the gravity force, and the other term are different types of additional gravity effects from GR that we commented yesterday. And we said that in this equation, we have the sound speed here, which is varying or depending over time. By equating these two terms, we can understand what is the 0 point of the oscillation. And as a matter of fact, we can find an approximate WKB solution for this equation, where we see that theta 0 oscillates around this 0 point with a cosine. I think it's a good time for giving a few more details on this argument here, and we will understand some physics from the arguments. So the argument of the cosine is k integral of Cs, which is a function of time, over d eta. And I can write this as 2 pi integral of Cs d eta divided by 2 pi over k. And this is very illuminating because here I have the integral over the sound speed. This is the sound horizon. It's distance traveled, so it's between 0 and some eta, and this would be a dummy variable. This is the integral between the early universe and the time of interest of the sound speed. So it gives you the distance traveled by a sound wave in coordinate space. So it is still the comoving sound horizon. While this is the comoving wavelength of the mode I'm interested in. Actually, I could multiply both the numerator and the denominator by the scale factor at the time of interest to make the numerator become the physical sound horizon computed at time eta. And then this would be the physical wavelength of the mode. And so I see that my cosine here has an argument which is 2 pi times the ratio of the sound horizon divided by the wavelengths. Can we make sense of this? if we would think in real space first, we should think that we have a propagation of acoustic waves, which are really pressure or density waves in the universe. So the wavelength is a distance between two wave crests, and this wave travels at the speed of sound. So the sound horizon is actually the distance over which a given wave crest would have traveled between the initial condition and a later time. And so the argument of the cosine is given by the ratio between this length and this length. How do you understand it? So a plane wave has a structure which is described by something like this, right? This is how you express your plane wave in real space. But when you go to Fourier space, this is absorbed by the Fourier transformation, and you are just left with the time dependence of the coefficient, or the real part of this, which is indeed a cosine. So this cosine here is actually this time coefficient describing the propagation of the wavelength. And this time coefficient can be seen as what you would see if you would be an observer sitting in one point. The wave would travel, and you would see the density going up and down in this fixed point. And it's clear, for instance, that if you sit at a given time in the universe, there is such a mode propagating, and the wavelength is equal to 2 times the sound horizon, then it means that you have seen 2 times the density passing through a maximum. If the wavelength is 4 times bigger than the sound horizon, you are sitting in a given place, then between the early universe and today, you have seen 4 times a wave crest passing by your location. So it makes complete sense that the argument of this cosine is nothing but 2 pi times this ratio. So this is what the argument of the cosine means. This will be very useful for understanding what follows. Okay, so then we started looking at a plot where we take a given mode k, and for this mode k, we are going to follow different transfer functions as a function of conformal time between the early universe, and here I'm not stopping the diagram today, but I'm stopping it soon after recombination or photon decoupling. And I remind you that we follow transfer functions. It means that we follow the actual solutions of the system of equations normalized to adiabatic initial condition with r equal 1. So the initial conditions for each function are given by a simple numerical factor, which can be read from the beautiful equality between all the perturbations in the initial condition. So for instance, we started with a metric perturbation psi. And if you would look at the initial condition, you would find that between psi and r, the adiabatic initial condition wants a coefficient 2/3. So it means that here, psi starts from 2/3. And then all the solutions that I will show do not come from the tight coupling approximation, but from the full solution from class. So this mode remains frozen on super Hubble scale, and at the approach of the Hubble crossing line, which is here, it decays. And we explained yesterday that there is an argument coming from the fact that you have pressure or not at a given time in the universe, which says that when a mode crosses the Hubble radius during radiation domination, the metric fluctuation should decay. When a mode crosses the Hubble radius during matter domination, it should not decay, because in this case, you don't have pressure, you have gravitational clustering, and this results in linear scale in phi being a constant. So now, for this mode k, the time of recombination is here, the time of equality is here. So clearly, Hubble crossing is during radiation domination, and that's why the mode decays at the approach of Hubble crossing. And this was for psi. The next function we need in order to understand our CMB is phi. We say that psi and phi are almost the same. Indeed, here you find a small difference. This small difference comes from the fact that here in the early universe, you have decoupled neutrinos and they have some shear. And that's why there is a small offset. This has a negligible signature on the CMB. We will ignore this detail. And knowing psi, I can predict now what should be the point around which my photon monopole should oscillate. It should be given by this function, 1 plus r psi, where r comes from the baryon to photon ratio. So during radiation domination, r is negligible, and I just have the dotted line being minus the yellow line, minus psi, and then r grows, which makes it a bit different, but it doesn't matter much. So what is important is that we have this shape for the 0 point of the oscillations. And now we launch photons in this system, and we normalize theta 0 to adiabatic initial condition. And given the relation we wrote for adiabatic initial condition, we had a relation between delta gamma and psi. There is also a relation between psi and r, and delta gamma is related to theta 0. Overall, you get a factor minus 1/3 between your photon monopole and the curvature perturbation. And minus 1/3 is not minus 2/3. So it shows you that inflation has prepared the fluctuation of the photon in the early universe, the overdensity of the photon, in a state which is not the state of the equilibrium of the tight coupling approximation. So it's like inflation putting things initially outside of mechanical equilibrium. If inflation would prepare theta 0 in this point, there would be no oscillation at all. But really, inflation has excited some modes which are really over densities and which are going to propagate like sound waves. So let's see what it gives. Now we let class compute the exact evolution of theta 0. And we see that on super Hubble scale, the solution is frozen. But at the approach of Hubble crossing, it starts to oscillate. And you see that it starts to oscillate around the dotted line. And so if initially you had some density contrast, the first thing that happened is an enhancement of this density contrast. You go to the equilibrium point, and because of inertia, you go over it, and then you go back, and you have this structure of oscillations, which can also be interpreted in the way we described before. Okay, so there is this minimum, there is this maximum, and after there is a period during which psi has decayed, psi is 0, and so the oscillations are nearly symmetric around 0, and they are nearly stationary with a constant amplitude. The phase seems to shrink, but this is because I'm using log scales. Okay, so I have at the beginning a stationary oscillation pattern, and then there is clearly a damping. We could imagine here that we have an exponential envelope for the oscillation. And this damping cannot be understood by looking at our previous analytical solution, because it was a tight coupling solution. Now we are close to recombination, and close to recombination, the tight coupling approximation breaks, and the important mechanism which appears is diffusion. We had this slide yesterday where we say that at the approach of recombination, the mean free path of the photon increases, and so it is rescattered. And at a given time, I can compute what is the typical distance traveled by a photon. And clearly, over this distance, you will lose any coherence of the primordial anisotropy pattern. The photon that you will observe at a given time, close to recombination, can come from any point in a sphere with such a radius. So they can come from points where they were initially over density, under density. So there is a smearing out of the fluctuation in such a sphere, and it means that the perturbation gets washed out. The tight coupling approximation cannot capture this effect, but the full Boltzmann hierarchy equation, which is exact, does capture the effect, and it does know about the finite size of the photon interaction rate. This term is implemented in the equation, so this effect will be consistently taken into account, and the result is the exponential damping of the modes when they approach recombination. But of course, this damping depends on the wavelengths of the mode compared to the diffusion length at recombination. If the mode has a wavelength much larger than the diffusion length, it will not be affected by damping. If it has a wavelength smaller than the diffusion length, it will be completely washed out. And clearly here, for this mode K, which is at a relatively small wavelength, there is a complete washing out of the fluctuation before recombination. All right, we understand psi, phi, theta 0 for this mode, but what do we need? We need, yes, I need to comment something else. And you might see something strange in this plot. You might see that at the beginning, the offset between the density fluctuation, or theta 0, and the 0 point of oscillation is small. But this offset grows after one oscillation. When you go down, you could expect that the minimum is at the same distance from the dotted line as here. This is what would happen if you would have a simple harmonic oscillator. And you see that it's not the case. Here we have a big dip, and this big dip must have some explanation. This explanation is precisely the role of the last two terms in our equation of evolution. We say these are dilation term related to the variation of the metric. And when the metric varies, this is a driving term that enhances, that provides energy to the system and that creates a larger amplitude of oscillation. And we see that this gravity boost effect is very clear. We will explain that the gravity boost effect occurs in a region which is around Hubble crossing. Due to the gravity boost effect, the mode does not go down to this point, but to this point. And when it goes up, it increases again the amplitude of the oscillation. And then you see that this effect should stop because the amplitude is stationary. So we have a region here where we had a gravity boost. This gravity boost at the end will explain why the CMB is sensitive to all the species in the universe. You could say that the CMB depends on physics in the baryon photon fluid, and that whatever else does not matter because it does not have interaction, like Thomson interaction, with photons and baryons. However, all the other species are gravitationally coupled with the photons and baryons. They play a role at the level of the gravitational force, and also they play a role at the level of this gravity boost effect. So if you change something with your neutrinos, your dark radiation, whatever, well, it will affect the evolution of the metric fluctuation, and it can make the gravity boost effect larger or smaller. So the very small detail for specialists, this would explain why the CMB reacts differently to extra relativistic species in the early universe when they are either free streaming or when they are forming a self-interacting fluid. So the gravity boost effect will be important at the end, and it makes a system sensible to everything else in the universe. Okay, so actually I already said this. I have this regime of symmetric and stationary oscillation, and then I have the regime of damped oscillation at the approach of recombination. Okay, so now we go back to our goal. Our goal is to understand all these terms, and now we have plotted only theta 0 for one mode. At least we should try to see what happens to the parenthesis, which is theta 0 plus psi. But I have theta 0 and psi, so to plot the sum, well, it's easy. I just need to sum the two curves, and my initial condition will be minus 1/3 plus 2/3, so it's 1/3, and I can plot theta 0 plus psi in cyan. So at the beginning, theta 0 and psi partially cancel each other. I have such a solution. And then psi goes to 0, so theta 0 plus psi coincide with theta 0 alone. So I get this pattern. I have an initial perturbation, an offset, and then the sign of the transfer function changes and changes again, and I have this pattern where the envelope of the fluctuation keeps increases, then remains stationary, and then is exponentially damped. Okay, next step, what if I want to understand the effect of the Doppler here? Then I need to understand theta b. Theta b comes from the velocity of the baryon, but if I have a tightly coupled photon-baryon fluid, theta b can be identified also with the velocity of the photon. And so I have a system in which theta 0 and theta b are like the amplitude and the velocity of the density perturbations. So they are like the position and the velocity of a harmonic oscillator. They both oscillate, but out of phase. So when the mode theta 0 is constant on super Hubble scale, the velocity vanishes. But then it oscillates with a phase shift of, as usual, pi over 2. Okay, and I'm not going to plot this because we already know phi m psi, so we can guess what their derivative will be from this pattern. Okay, so that was for one mode. Now I'm going to do the same, but for all modes at the same time. I will use plots where the color level will reflect to the intensity of the transfer function, and I start from phi, which I can think to be equal to psi. And because I want to show all modes, now I have the time flowing from the early universe to the time, now it's the time today. And here I have my wave numbers. Characteristic times here are the time of equality between matter and radiation, the time of recombination or photon decoupling, the time of equality between matter and lambda, and the lower axis is today. And what we had before was like a vertical cut, a vertical slice in this plot for a k of, I think it was 0.5, so it was around here. And indeed, we started from a plateau, and then phi m psi were going down to 0. And here, so the red means 2/3, and the blue means 0. So what do we see? We see a pattern like this. Everything on top of the gray curve is a high constant value of psi. Everything below the gray curve is 0. And we can understand it in this way. The modes with a large k or a small wavelength cross the Hubble radius deep inside radiation domination. And so as soon as they approach the Hubble radius, they start to decay, and then the psi and phi are completely washed out and remain 0 until today. Instead, if we look at very small k, which means very large wavelengths, these very large wavelengths cross the Hubble radius deep during matter domination, and then they remain essentially constant. There is a negligible decay for this mode, and the reason is what we said yesterday. When this mode crosses the Hubble radius, we already have linear structure formation. The total density contrast increases proportionally to the scale factor, and due to power counting arguments in the Poisson equation, we find this beautiful cancellation between the effect of gravitational clustering and of the expansion, which makes phi static. So phi remains constant. If we would zoom in this small region, which is hardly visible, we would see that this is no longer true below the line of equality between matter and lambda. Below this line, phi decreases again on all scales. And you can understand it from the fact that during lambda domination, lambda is a species that contributes to the expansion of the universe, but not to local gravitational force because it's homogeneous. So lambda breaks the equilibrium between gravity and expansion that we had during matter domination. And it cannot support the metric fluctuation like during matter domination. So the metric fluctuation decay again. And they don't reach 0 by today because it's a slow process. But if we would wait in the future, at some point, phi would reach 0 on all scales. Okay, what do we do with this? We can notice first that in the equation before, what played a very big role was the partial derivative of the metric with respect to time. So we have a non-zero phi prime on this plot whenever on a vertical direction we have a gradient of color. If we have a gradient of color before recombination, it can contribute to the gravity boost. After recombination, it can contribute to the integrated Sachs-Wolfe effect. We see that before recombination, we have a gradient of color along this line, which is roughly like the Hubble crossing line. It's a bit before, but it doesn't matter. It says that when a mode approaches the Hubble radius, it decays. And so this is a region where the gravity boost will take place. It means that when you look at the evolution of a mode, the amplitude of the oscillation is only enhanced at the beginning when the mode crosses this region. And when it exits this region, there is no more gravity boost, and the amplitude of the oscillation can become stationary. But now the other question is, when do I have an integrated Sachs-Wolfe effect? For this, I need to be after recombination because it's an effect on the light of sight of the decoupled photons. And I need to have these vertical gradients. And we see that overall, we have no vertical gradients. And that's really nice, as we said yesterday. That's the reason for which the CMB photon gives us an image of mainly the last scattering surface and not of nearby structure, which would be the case if this phi was varying with time all over the place. However, there is still a small gradient here for modes that cross the Hubble radius soon after recombination, because these modes live at a time which is not very far from the time of equality. And for this reason, phi is not completely stabilized by the argument of linear growth of matter during matter domination. So here there is a bit of a gradient, and this region will be responsible for the early integrated Sachs-Wolfe effect. Then the other region where we have a gradient is during lambda domination. Here phi decays, and this region, when the mode will cross this region, they will contribute to a late integrated Sachs-Wolfe effect. I think we have exploited all the nice information from the plot showing the transfer function phi. Now let's do the same for the plot showing the transfer function theta 0. And that's where most of the CMB physics can be seen. We have the Hubble crossing line. This yellow line is a sound horizon crossing line, but doesn't matter. Let's not complicate, and let's mainly look at the Hubble crossing line. We see that well above the Hubble crossing line, theta 0 is constant and reflecting the static adiabatic initial conditions. But we see that at the approach of the Hubble crossing line, we have a sequence of oscillations. And it's like when we looked at a single mode. If you follow a single mode, first it has some density contrast, and then you see that the density contrast gets enhanced, then inverted, inverted again, inverted again, inverted again, inverted again. And we have this sequence, which is a sequence of oscillation given by the cosine of this argument. So if I look at a large k, which means a small wavelength, then between the early universe and the time of recombination, this large k has the time to oscillate many times. It's similar to the explanation I made here, because an observer would see many wave fronts of sound waves passing by. While if I look at a smaller k, which is a larger wavelength, it has less time to oscillate until recombination. So that's really interesting. What else do we see? So we are interested at the end in the value of theta 0 at the time of recombination. This is what will show up in our line of sight integral. So we are interested in the dependence of theta 0 on k at a fixed time here along this line. But we see also that in these plots, if you use log-log scale and you arrange your axes well enough, you get a symmetry such that the pattern on vertical cuts is the same as the pattern on horizontal cuts. Well, it makes a lot of sense. It's because you have a cosine. The oscillations are described by a cosine of k times this integral. But CS is almost constant. It just decays a bit at the approach of recombination. If I take CS to be constant, this integral, which should be written like this in principle, will become kcs eta. So it features the product k eta. And for this reason, you have this symmetry. Everything is perpendicular, is parallel to lines with a slope of 45 degrees. And if you do a cut into this surface on a horizontal line, it will look like the cut on a vertical line. So when we will be interested in the dependence of theta 0 on k, it will look very much like in the previous plot we had, where we had fixed k, and we looked at the dependence of theta 0 on time. What else can we say? Yes, sure, yeah. Yeah, Yeah, that's a free streaming solution. Once the photons are decoupled, they free stream, and in the free streaming solution, each multipole has damped oscillation, and here you see the damped oscillation of theta 0. Yeah. And you would have an analytical approximation for these given by Bessel functions. Yeah. Okay, another interesting thing is that here you see below the blue line, everything becomes gray, and gray means 0. What is the blue line? It's the line corresponding not to Hubble crossing, but to the crossing of the diffusion damping scale. The diffusion damping scale is this quantity, giving the typical distance traveled by a photon. It was defined mathematically on one of the slides of the first lecture as an integral. And being below the blue line means looking at a mode whose wavelength is smaller than the diffusion damping scale. And as expected, below this line, all the fluctuations are watched out by the smearing of the fluctuations on small scales. So I think the picture makes some sense now, and you can already anticipate now where the CMB peaks come from. They come from the fact that we will at the end take a picture of the state of the Fourier mode on this line. Some modes have had no time to oscillate. Some of them had time to oscillate over half a period, 1 period, 1.5, 2, 2.5, 3, etc. And this will give you the sequence of the peaks, which will be damped at some point. But let's go slowly, step by step, and let's look first at this new plot. At first sight, it's the same plot as before. But in fact, it's not, because before I was fixing a K and looking at its evolution as a function of time. Now I'm doing the opposite. I'm fixing the time of decoupling, and I'm plotting transfer function at the time of decoupling as a function of K. It looks like before because of this symmetry. So now we can comment on the different curves. Phi m psi have this structure where they are constant, and then they are washed out for the large K, because the large K have crossed the Hubble radius during radiation domination. From phi m psi, I can define the 0 point of oscillation now at the time of decoupling. It has a pattern -1 plus r psi, and it looks like this. It's like, in fact, psi multiplied by a negative coefficient, with r taking its value at the time of decoupling. So we have this pattern, and we expect that the oscillation of theta 0 are centered on this pattern. Then we show theta 0, and it's exactly what we thought. Here we see modes that did not have time to oscillate, mode that had time to oscillate by half a period, 1 period, 1.5, 2, 2.5, 3, etc. And we see that the maxima and the minima are centered around the dotted line as expected. Next, we combine theta 0 and psi to form the sum, theta 0 plus psi, and it has this pattern with a plateau, with then large oscillation. The amplitude of the oscillation is fixed for a while, and then it goes down. We could also plot theta b, the baryon velocity. At the time of decoupling, we would get 0 for super-Hubble modes. And for sub-Hubble mode, we would see again some frozen oscillatory pattern, which would be out of phase with the patterns in theta 0. Okay, so now we are going to see how to go from this plot to the CLs. And what we expect is that the CL come from an integral over modes. We have seen it before. But we said, the CL should feature a one-to-one correspondence between values of L and values on K at last scattering. So we expect that in very good approximation, 1K in this plot will contribute to the CL at 1L. If this is true, if I plot my CL here, the pattern in the CL will look like the square of this function. Why the square? Because the CL contains the square of the transfer function. So my CL should feature things like the square of theta 0 plus psi. provided that I scale my axis for CL in such a way that the value of K here project to a value of L here. So this is what we are going to do in 2 steps. First, starting from this curve, I identify theta 0 plus psi, which is the most important transfer function for the CMB, and I square it. And the square gives me this with a plateau, a 0, first peak, second peak, third peak, etc. Between the peak, the function goes through 0 again, and we can comment a little bit on the amplitude of the peak. You see that the amplitude of the peak is very non-trivial. We have a large peak, a small peak, a large peak, a small peak, and then all the peaks go down. Why do we have this structure? Well, if you look here, you see that between 0 and the minimum, I have a lot of space. Between 0 and the maximum, I have less space. Here I have more space. Here I have less space. And this reflects in the amplitude of the squared peaks. And what is the physical reason for this? The physical reason is that the blue function is not oscillating around 0, but around an offsetted curve. And the offsetted curve is set by the 0 point of oscillations. So the 0 point of oscillation that we described yesterday as being the signature of a competition between gravity and pressure forces in the fluid will lead to the asymmetry between the odd and the even peak. Once psi goes to 0, the peak becomes symmetric, and there is here a short range in which the peak look indeed symmetric, but then they are damped by a kind of exponential envelope, and this comes from the washout by diffusion damping. Now let's try to see if this does look or not like our CL curve. So I plot here the CL curve, but it's not the full CL. I asked class, and you can do it on any notebook, even on the public notebook. You can ask class to plot the CL that you would get if you would select only one of the terms in the line of sight integral. And here, we only select the contribution to the CL that comes from the combination theta 0 plus psi, which is a Sachs-Wolf term. So here we have the CLs normalized in some way. If you ask me to explain the normalization, I can do it. And here we have the multiples, but we have rescaled our multiples by this factor because we have in mind the one-to-one correspondence between L and K's that we have derived yesterday. It was like this. Eta 0 minus eta dec. So here I have rescaled my multiple axis by this number such that one multiple L should match 1K here. Then does it work? Well, it kind of works because the structure of the CL is very similar to the structure of this squared transfer function. Of course, there are some differences. And the differences, I mean, by eye, are the fact that you don't go to 0, and the fact that the contrast between the plateau and the peaks is not as big, and the contrast between different peaks is not as big in the lower plot than in the upper plot. So you could say that this looks like a smoothed version of the upper plot. When you do a smoothing of a curve, you decrease the contrast between maxima and minima, and this is what occurs when you go from here to here. So our picture that there is a one-to-one correspondence is only approximate. In fact, there is a smoothing. And the smoothing has several origins. There is a smoothing which takes place along the line of sight and a smoothing that takes place orthogonal to the line of sight. The smoothing along the line of sight comes from the fact that we treated the last scattering surface as a real sphere. But because the decoupling of the photon is progressive, in fact, the last scattering region is a thick shell corresponding to different values of time. So in your projection, you should not choose a single value of time here, but you should integrate over a short time range. And this will introduce some smoothing in our previous picture. The other smoothing is orthogonal to the line of sight. We say that even if I have one wavelength, these wavelengths will contribute mainly to one multiple, but not only, also to neighboring multiples. And this is a smoothing in angular space. And the combination of these two smoothing is such that the true CL appears as a smoothed version of the square of the transfer function. Okay, that's nice, but it only gives us one term in the CLs, the Sachs-Wolfe term. Let's try to guess what is the contribution of the integrated Sachs-Wolfe term. We expect a contribution from these two regions, the early and late integrated Sachs-Wolfe. Let's try to anticipate where we will see such a contribution. We see that the early integrated Sachs-Wolfe term is important for modes which cross the Hubble radius soon after recombination. These modes should be not very far from the mode that contribute to the first peak. The first peak comes from a pattern that we have seen here in the plot of theta 0. Instead, the late integrated Sachs-Wolfe effect is for very small values of k, and moreover, it takes place very close to us, so it projects under very big angles. So we should expect to see this effect showing up at very small values of L. And let's check it. Now we ask class to plot only the contribution to the CL from the early integrated Sachs-Wolfe. It gives us this red curve, which peaks close to the first peak here. Or it depends, well, this is the first peak in the CLs, but in terms of oscillation, the first oscillation was here, the second was here. So it peaks in between. And then the late integrated Sachs-Wolfe effect gives a contribution which peaks at the smallest observable value of L, which is a quadrupole. And then it goes down. So this contribution will be important because it is going to tilt the plateau that we had here. Now we have shown three contributions, one is missing. The one which is missing is a Doppler contribution. The Doppler contribution comes intuitively from the square of theta b. So I don't show here the square of theta b, but it should give me 0 in this region and then a series of peaks that should be out of phase here. And indeed, the contribution to the CL of the Doppler is 0 here. And then it gives me peaks which are out of phase with the blue peaks. Now, to get the full CLs, what should we do? We should sum up these effects. If I take these four curves and I sum up, I will get something which looks like the total CL, but not quite. Why? Because in fact, these different transfer functions sum up inside the calculation of theta L. And when I take theta L square, I also have cross term. So in principle, we could plot CL contribution coming from the cross correlation between the blue and the red, the blue and the yellow, etc. I'm not plotting this cross term because the curve would become messy, but I directly plot the total, and up to this cross term, the total looks pretty much like the sum of the different curves. In particular, it starts with a plateau, which is tilted by the late integrated Sachs-Wolfe effect. Then there is a rise to a first peak rather than a depletion. This is because when we would expect a depletion from the Sachs-Wolfe term, we have a compensation coming from Doppler and early integrated Sachs-Wolfe. So instead of going down, it goes up, and the way in which it goes up is actually very much impacted by the detail of the early integrated Sachs-Wolfe effect. So if you have a cosmological effect changing the early integrated Sachs-Wolfe, like for instance, massive neutrinos, it will change the shape of the rise to the first peak. Then you have the first peak, the first dip. The first dip is non-zero for the reasons we have seen, Doppler and smoothing of Sachs-Wolfe, third peak, etc. And if we look at the amplitude of the peaks, the first peak is very big because for the first peak, we have a very big offset here due to the 0 point of oscillation being shifted. And additionally, we have a contribution of the early integrated Sachs-Wolfe. So the first peak is a winner. The second peak is penalized by the shift of the 0 point of oscillation. So it is smaller. The third peak could be expected to be larger because now it is enhanced by the 0 point of oscillation, but it doesn't get an early integrated Sachs-Wolfe contribution. So overall, it ends up being comparable to the second peak, but for the cosmological parameters that I choose. If I would change the cosmological parameters, all these amplitudes would go up and down a little bit. And then the other peaks are consistently decreasing with an exponential envelope. And now we understand qualitatively the shape of the CLs. So we have made a lot of progress, and we did the hard part. The hard part was to understand all these physical mechanisms, gravity boost, 0 point of oscillation, etc. Now we can get the fruits of our effort, which is the fact that now we can get an easy understanding of why the CMB spectrum depends on all the cosmological parameters and how. So because of time constraints, which are fair, I'm going to look only at the minimal lambda CDM model. But we could extend our discussion to massive neutrino, extra relativistic degrees of freedom, annihilating dark matter, all the nice things that you are seeing in the Beyond Standard Model lecture. But we won't do it here, we don't have time. So we take a flat Friedman model with omega k equals 0, with a plain cosmological constant, with minimal cold dark matter, we neglect neutrino mass effect, we fix the amplitude of relativistic species, we take a power law primordial spectrum, and then we have to choose a basis for our lambda CDM parameter. And of course, there are different choices of independent bases. And I choose one because it's a pedagogical choice. The parameters that I choose here are really directly imprinting the shape of the CMB spectrum. So for lambda, the cosmological constant, I choose to account for lambda with a big lambda, the fractional contribution of lambda to the critical density today. So this parameter tells me essentially when is the transition from matter domination to lambda domination, at which redshift. For physical components like baryons and total matter means baryons plus cold dark matter, I choose a small omega, which is a combination big omega h square, and this h square is motivated by multiplying with a critical density. You know that this combination is a nice parameter because it's really proportional to the physical density, rho x, of the species x today. You have the contribution of the fractional density, the contribution of the critical density, and the combination is a dimensionless parameter accounting for the true physical density of these components today. So I take a small omega b, a small omega matter. Then I need, we have neglected in the previous slides, we have neglected the effect of reionization, but we will need to restore it at some point. And if you remember the first lecture, we said that when we plot the optical depth has a plateau at tau rho, and the amplitude of this plateau is really the quantity which tells me which fraction of observable CMB photon last interacted at recombination and which fraction last interacted instead during reionization. So this plateau is tau rho, the optical depth to reionization. And then for my primordial power spectrum, I have an amplitude parameter and I have a tilt parameter. And what we are going to do is fix all these parameters but one and see how the CMB spectrum changes, and then try to get a physical understanding. And I start with the easiest one, which is the overall amplitude. Of course, if you remember the CLs are given by an integral over k of the square of the photon transfer function. Sorry, I changed notation. Imagine that I plot the temperature spectrum, then I would replace x and y by t. This would be delta LT, and in my previous slides, delta LT was just called theta L. I changed notation here without noticing. So my CL is given by an integral over decay of theta L squared times the primordial power spectrum. And the primordial power spectrum is given by an amplitude times the power law with a tilt. And so obviously, this amplitude here is an overall factor. If I change the amplitude, I just renormalize my whole CMB spectrum. So that's completely trivial. So in each of these plots, the black curve is a reference lambda CDM model. It's with the best fit Planck parameters. And then increasing levels of red means the spectrum that you get when you increase the value of one of the parameters. So this one we understand. Then NS is also fairly trivial. When you change NS, you change the tilt here, so you introduce a different power law in this integral, and this power law will give more weight to small k or to large k, right? You can have NS be smaller than 1, it's a red tilt, and you give more weight to small k. NS bigger than 1 would be called a blue tilt, you would give more weight to large k. So, obviously, because you have an approximate correspondence between values of k and L, if you give more weight to small k, you give more weight to small l, and you tilt your spectrum. But now, in the red curve, I increase NS. So as I increase NS, I give more and more weight to large k, large L. So I tilt my overall spectrum like this. Two remarks. First, in my plot, there is no effect in the middle. That's just due to an arbitrary choice of a pivot scale. When you parameterize your primordial curvature spectrum, you need to choose a pivot scale, which is a scale at which you decide that the amplitude is given by AS. And then this scale will naturally appear in this ratio, and it's really your choice. Of course, once you have fixed the pivot scale, you see that if you change NS with a fixed AS, you then don't change the primordial spectrum as the pivot scale. Now, here there is a choice of pivot scale such that it projects to an L of about 600 or 700, and that's why there is no change here, but it's completely arbitrary. Second, you see a big effect on small l and a small effect on large L in this log-log plot. Why? It's because in my integral here, I have an exponential cut in the transfer function coming from diffusion damping. And when you multiply an exponential with a power law, the exponential always wins. So it means that increasing NS will not give you a significant enhancement here because the exponential is always there to wash out the modes. Okay, now a bit more, much more interesting, very interesting, the effect of omega b. The effect of omega b is more complex. You see that the peak shifts to the right, and the first peak goes up, the second peak goes down, and the other peak go to the right. So there is a lot to understand here. I'm writing here the three most important effects. The first important effect comes from the 0 point of oscillation. We say that the 0 point of oscillation, which gives the offset and the contrast between odd and even peaks, depends on this function. And in this function, R is a baryon to photon ratio that we need to estimate here at the time of decoupling. So you could live in a universe with a large omega b, and this would mean that this ratio is large at the time of decoupling, because this ratio is really rho b over rho gamma. Rho gamma today is fixed by the measurement of the temperature of the CMB, 2.7 Kelvin. Rho b is fixed by your parameter omega b. So when we change omega b, we directly change the value of R at recombination. With a bigger R, you see that the 0 point of oscillation is more shifted, so you get more contrast between odd and even peaks. And that's why the first peak goes up, the second peak goes down, the third peak goes up. You don't see this trend on higher peaks because for higher peaks, the dominating effect is always a damping effect. I forgot to say the damping effect with this exponential envelope is called silk damping, by the way. So for high peak, I don't see this pattern going on because silk damping always takes over. Now, what about the scale of the peak? We have seen that the scale of the peak corresponds to, intuitively, what determines the scale of the peak is the value of k at which I have maxima and minima. So it's the value of k for which this would be 1, and the phase of my cosine would be 2 pi. So it means that I have a peak for the modes which are equal to the sound horizon at decoupling. If I have a model in which the sound horizon is shifted, then the wavelengths which imprints my mode will be shifted, and these wavelengths will be seen under a bigger or a smaller angle. To summarize, the scale of the peak corresponds to a multiple that subtends an angle theta equal to pi over ls. And this theta, this angle theta, should be the angle under which I see the sound horizon on the last scattering surface. The sound horizon on the last scattering surface is ds at the time of decoupling, and I see it under an angle which should see the sound horizon divided by the radius, but we are in cosmology, so we don't use the radius. We use the angular diameter distance to the last scattering surface. So we get this ratio. This ratio can be matched to pi over ls, where ls is the multiple of the peak. And why should omega b change this quantity? Is it explained? Yeah, sorry, I was going too fast. So this was a plot to explain the first effect with the 0 point of oscillation. If I increase r, then my dotted line goes down. I have more contrast between odd and even peaks. We already explained this. About the angular scale of the peaks, I don't have additional slides. So the sound horizon is given by the integral of the sound speed over time. The sound speed was equal to 1 divided by 3 times 1 plus r. So there is an r in the sound speed. If I change the value of omega b, we said we change r at recombination. So we change also the value of cs at recombination. We change the sound horizon. So the sound horizon is seen under a different angles and our peaks are shifted. You could take this reasoning slowly on a sheet of paper, and you could even try to understand why, if you increase omega b, the L of the peak increases. It's fairly easy with the reasoning that I just gave and when writing the equations. The third thing that we observe is that the damping envelope here, assume that you plot the damping envelope. You try to plot a line that goes through all the maxima of the black curve, and then a line that goes through all the maxima of the red curve. And you see that these lines will be offset. Damping in the red model takes place at larger L, which are smaller angles. And for computing this damping envelope, you can carry exactly the same reasoning as I did. You can say that if I define an angle theta d, which would be pi over LD, this angle would be the angle under which we see the diffusion length at last scattering. So you can get an equation similar to this one, but replacing ds by the diffusion length that we computed in a slide in the first day. And this gives you really the scale of the damping envelope. It gives you an LD, and then the damping envelope can be thought to be a factor minus L over LD squared, something like this. This is how you would approximate analytically the effect of silk damping. So theta b changes the position of the peak, the position of the damping envelope, and the contrast between odd and even peaks. Now let's try to do the same for omega m. This is maybe the most difficult, and then the last two will be simple again. So for omega m, when I increase omega m, I see several things. I see that all my peaks are going down now. They are shifted in the other direction when I increase omega m. And the damping envelope is also shifted to the left, smaller L, larger angles. Now we have all the key ingredients to understand why. The first two are similar to the effect of omega b. They just have a different amplitude. First, we see that the peaks are shifted. So we anticipate that probably the sound horizon depends on omega m. And indeed, the sound horizon is given by this integral from 0 to eta of the sound speed times d eta. The integral looks very simple when you express it as an integral over d eta. You could do a change of variable to express it as an integral over a or over z. And in this case, you would see explicitly that there would be a factor h appearing, the expansion rate. So when you integrate, when you express the sound horizon as an integral over a or over z, the integrand contains both the sound speed and the expansion rate. an advantage of using conformal time is that it kind of absorbs the expansion rate. Once you have the expansion rate here, it's clear that your sound horizon depends on the expansion rate at all times between the early universe and the time of recombination. However, recombination takes place at the beginning of matter domination. So part of your integral is during radiation domination and part is during matter domination. And the transition between the two is set by the redshift of equality between matter and radiation, which is actually a function of omega r. The redshift of equality depends on the ratio between the matter density and the radiation density. The radiation density is fixed in the standard cosmological model by the fact that you measure the photon temperature and you assume n effective to be 3. But the matter density is not fixed. It's parameterized precisely by omega m. So you can view this omega m as precisely the free parameter that determines Z equality. If I change Z equality, I integrate over more or less radiation domination, more or less matter domination. I change my sound horizon. This is responsible for a change in the sound horizon and for the scale under which I see my CMB peaks. For the damping envelope, it's quite similar. If I express my damping envelope, we could go back to the first slide. It was also an integral between the early universe and time eta, but with a different argument. In the argument of the damping envelope, you would also find the expansion rate. However, you would find it with a different exponent than in the sound horizon. So the sound horizon and the diffusion scale both depend on the expansion rate, but differently. Nevertheless, when I change omega m, I change this expansion rate because I shift the time of equality. So I also change my damping envelope, and this is why the damping envelope here is shifted to the left in the red case. And what we have not yet explained is why do the peaks go down? The peaks go down for two reasons. This is the most subtle part. If we change the redshift of equality, we change the range of scale, which are affected or not by gravity boost, and we change the intensity of the early integrated Sachs-Wolf. I forgot if I have a slide explaining it. Yes, I have everything to explain it here. Okay, so in these lines, we have here conformal time going up when we go downwards. We have the line for the time of equality. We have the line for the time of recombination. Recombination always takes place at the same time. This is fixed by the psi equation. It has a logarithmic dependence on some cosmological parameters. We will neglect it. So time of recombination is fixed. Time of equality depends widely on omega m. So when I change omega m, this black curve goes up or down, meaning that I have more or less time between equality and recoupling and recombination. But the gravity boost effect is important during matter domination. So if I shift this curve upward or downward, there will be some intermediate scales here that in one model will cross the Hubble scale during matter domination. In the other model will cross the Hubble scale during radiation domination. In one model, they will lead to a gravity boost. In the other model, they will not lead to a gravity boost. And this explains a big amount of this effect. These intermediate scales here are precisely the scales that live around this equality crossing line. And so depending on the equality taking place a bit earlier or a bit later, they are more or less affected by gravity boost. You see that when I increase omega m, the amplitude goes down. This is because these modes do not experience so much gravity boost anymore. The other reason is from the early integrated Sachs-Wolf. We say that even after recombination here, we have a gradient because these modes after recombination live at a time which is not so far from equality. So phi is not yet completely stabilized, and I have some phi prime and some integrated Sachs-Wolf. If equality takes place very close to recombination, then here I still have a wild variation of phi and a lot of early integrated Sachs-Wolf. If equality takes place very early, then at recombination, phi is completely stabilized, no early integrated Sachs-Wolf. And we said that the early integrated Sachs-Wolf is important at the scale of the first peak, and this is why the effect on the first peak is bigger than on the second peak. You could wonder if these two effects collaborate or are antagonists. It turns out that they collaborate. So when I change omega m, when I increase omega m, the two effects want to lower the peaks, but this is mainly true for the first two peaks. The other ones are unaffected by this effect. Okay, we understood 4 of the 6 effects. The last 2, okay, the next one is easy, omega lambda. Okay, I see now that there is a region where the effect is completely trivial. All my curve goes to the left, but its shape is unaffected. Instead, here it's less trivial. My plateau is more and more tilted when I increase omega lambda. Okay, easy to understand. Omega lambda is a parameter that controls the redshift between matter and lambda. So it changes the evolution of the late universe, not of the early universe. In each of these ratios, you have a ratio of integrals. On the numerator, it's always an integral in the early universe between initial conditions and decoupling. On the denominator, it's the angular diameter distance, so it's an integral over the late universe between decoupling and today. When I change omega lambda, I change clearly this integral. If you write dA as an integral in your integrand, you will have the expansion rate. So if you change the transition between matter and lambda, you change the integrand. But so lambda acts on the denominator. So it acts exactly in the same way on these two quantities. And you could even go beyond this. You could say, oh, it's just changing the correspondence between one value of k on the last scattering surface and one value of L, because it changes the angular diameter distance. So it's a trivial effect of moving the whole curve to the left. The last scattering patterns are the same, but the angle under which we see them is changed. On top of this tilting comes from the fact that if I increase omega lambda, my lambda domination starts earlier. So my metric fluctuation have more time to decay during lambda domination. I have more late integrated Sachs-Wolf, and we have seen that the late integrated Sachs-Wolf has this typical pattern. Unfortunately, this nice effect is difficult to measure precisely because this is where cosmic variance is large, but still we have constraints on this. Okay, I'm just left with one effect, the effect of reionization. And so far we completely neglected reionization, so it's time to say in a sketchy way what reionization is doing. Before going to the physical explanation, you see that reionization is just decreasing the amplitude of my spectrum on all scales, except the smallest L's. Why? I need to remember what is in the next slide first, sorry. Only one, okay, yes, okay. In the line of sight integral, our Sachs-Wolf term was multiplied by a visibility function. And we said, okay, let's pretend that this visibility function is a Dirac function peaking at recombination. And when we did this, we neglected completely reionization. However, at some point, we have plotted the true visibility function as a function of eta, and we say that there is a recombination peak, and then there is a reionization peak. And the surface between the curve is 94%, 6%. Well, actually, these numbers depend on the precise value of tau rho. This is what tau rho is governing. Okay, so we did as if we had a single peak here. Now, let's try to restore the truth. And the truth is difficult to model, so I will do one more approximation. I will put a Dirac peak here, a Dirac peak here, but with some weights such that the area when I integrate this peak is still 0.94, and the area when I integrate this peak is still 0.06. So to get this, I derive an approximation of my visibility function, where I have the Dirac peak at decoupling multiplied by the surface below this peak, which has to be exponential minus tau rho. And this is very clear from one of the first slides when we explain how G was connected to tau rho. And I have a second Dirac peak with a weight given by the probability that the photon last scattered at reionization, which is 1 minus exponential minus tau rho. Okay, so if I have more or less reionization, if I increase tau rho, the exponential minus tau rho will decrease, this parenthesis will increase, and I give more weight to the second peak. So let's assume that we would repeat the arguments that we had before, but with such a corrected visibility function. We would go back to the line of sight integral, and in the line of sight integral, we had terms like integral over d eta between eta in E and today, of G of eta, and then we had theta 0 plus psi, and we had our Bessel function. And before here, we took a Dirac at recombination. So we said, no, I just can eliminate the integral and look at theta 0 plus psi at recombination. With this change, we could decompose G of eta in two terms. The first term would be exactly like before, but with an overall coefficient here, exponential minus tau rho. So I would get like an overall factor in front here, exponential minus tau rho. And this overall factor would renormalize my theta L. The CL depends on theta L squared. So they have the square of this as an overall coefficient. And it means that if I would keep only the first term, I would expect my CL spectrum to be renormalized by the square of this, which is exponential minus 2 tau rho. And in models where reionization takes place earlier and earlier, tau rho is bigger and bigger. This coefficient is smaller and smaller, so my spectrum goes down. And this is what we see. The spectrum is going down here. This is a mathematical explanation. Do we have a physical understanding? Yes, we do. If we increase tau rho, it means that we give more and more weight to this peak, less and less to this one. It means that we have a smaller fraction of the CMB photons that we observe that originate from the last scattering surface, and a larger fraction that originate from reionization. But the photons that come from that last scattered at reionization do not carry a structure with this correlation and these peaks. They are much smoother. So we have a washing out of our spectrum. A lower spectrum means less correlation, less angular correlation, because we have less contribution from correlated photon and more contribution from uncorrelated photon. And this is why we have this overall factor. You see that this argument does not work on small l, and this is where the second term comes. Suppose that I would plug the second term here. I could say that up to this overall coefficient, I have a Dirac of delta eta minus eta rho. And so I get a second contribution, which is like the first CMB contribution, but with everything evaluated at reionization. It's like if you had a second last scattering sphere, but much closer to you. And on this sphere, again, you would have some physics with a Doppler effect, with a Sachs-Wolf effect, etc. And so this will produce its own power spectrum, which will be decorrelated from the initial one, but you will observe only the total. And then the total CL looks like this. If you had no reionization, you would get a pattern. Because you have reionization, you have a contribution from two terms, correlation from recombination and from reionization. The correlation from recombination looks the same, but with a smaller amplitude. Oh, you cannot see that it's a different color, sorry. Okay, the contribution from recombination is the same, but decreased by factor -2 tau rho. The contribution from reionization will be another spectrum that you can compute, but intuitively, because the reionization scattering sphere is very close to us, any correlation will be seen by us on very large angles. So the second contribution would have a shape which would be something like this. Then you can enter into details to justify the shape, etc. And when you sum up the two, there is a kind of coincidence that makes the total of these two equal to the spectrum without reionization. It's not even equal. In fact, if you zoom here, you will see that the red curve is larger than the black curve because the contribution from correlation at reionization does more than compensating the suppression induced by reionization on other scales. But overall, it looks like a step-like suppression. It looks like you have a negligible effect here, and then a step, and then a constant suppression factor. And this is the effect of reionization. And if we put everything together, we see that when we vary the 6 cosmological parameters of our model, we get effects which are really different from each other. Look only at the left first. To be sure that they are independent of each other, you would need to do some kind of joint fit. But already we have the intuition that these effects are sufficiently different to be non-degenerate in the sense that you cannot represent one effect by a combination of the other. Omega B is the only effect that changes the amplitude of the first two peaks in an asymmetric way. The only one. Omega M is the only parameter that acts coherently on only the first two peaks and not the other. AS is the only one acting on the amplitude, and is the only one doing an overall tilting. Tau rho is the only one with a characteristic scale of a step-like suppression around here. For omega lambda, it's less obvious, because you could say, oh, this shift here can probably be obtained by a combination of the others, but at least you have the late integrated Sachs-Wolf effect, which is distinct. Arguably, the late integrated Sachs-Wolf effect is difficult to constrain because of cosmic variance, but still you can constrain it. So this forms a basis of 6 independent effects. So you have 6 parameters, you have 6 different effects. It means that if you do a single measurement, you can measure, and you assume that this model is correct, you can measure the 6 parameters. When I do this course in more time, I insist on the fact that if you want to understand the shape of the CLs in standard cosmology, it comes from a combination of 8 physical effects. There is an effect which is the angular scale of the peak, theta s, which is this pi over ls, so ratio of sound horizon over angular diameter distance. There is the effect that is related to R at recombination, which comes from the balance between gravity and pressure, or between baryons and photon at recombination. There is the effect of shifting the time of equality relative to the time of decoupling. There is a scale under which we see the damping envelope, which comes from the ratio between the damping scale and the angular diameter distance. There is a global amplitude, a global tilt. There is a breaking of the horizontal plateau by the late integrated Sachs-Wolf, and there is a reionization step-like suppression. So 8 effects. But of course, these 8 effects in the lambda CDM model are not independent because they are controlled by 6 parameters. That's not a problem. It's very nice. The fact that you have more effects than parameters means precisely that with a single measurement, you can measure all the parameters. Now, you could wonder if this nice statement that with a single measurement you measure all your parameters would hold in extended cosmologies. And you could say, in extended cosmology, I will have more and more parameters. So at some point, the effect of some parameter will be equivalent to a combination of others. Usually, it's not the case, because In the most unlucky case, when you add a parameter, you don't change the number of physical effects at play. And there is a famous example, it's omega k. When I change the spatial curvature, I have one more parameter, omega k, but I don't have more physical effects. It's just that omega k is one of the parameters that controls, for instance, the late integrated Sachs-Wolf or the angular scale of the peaks. But nicely, I have a bit of margin. I have here 8 effects for 6 parameters. In a model with curvature, I have 8 effects for 7 parameters. I'm still on the right side, and I can measure all my parameters independently. That's why you get constraints on omega k from CMB alone. But most of the time, when you play with massive neutrino, n-effective, tensor mode, running of the tilt from inflation, and all additional physics that you can put, usually you will also add to the list more physical effects, which will leave a distinct signature. So very often, even when you go beyond lambda CDM, you still end up with a non-degenerate situation. And so this is why the CMB is so powerful. And that was only with temperature. The situation is even better when you add polarization. And this will be the topic at the beginning of the next lecture. So in the next lecture, we will become much more qualitative. We cannot give details on everything. So for the temperature, I try to give quite some details. Then we will become much more qualitative and understand why there is polarization intuitively, and then why tensor modes leave an imprint. And then if there is time, we will talk a little bit either about CMB spectral distortions or CMB lensing. I can do a poll. I will ask, who is more interesting by CMB spectral distortion? Who is more interesting by CMB lensing? Spectral distortions. Okay. CMB lensing. Oh, okay. Yes. Ah, I had prepared the other one more, so more work tonight. No, okay. Okay, very good. Thank you very much. We have a few minutes for questions. So you are always free to choose a parameter basis that you want, provided that all the parameters are independent. For instance, I did not have H in my list of parameters here. And maybe some of you were disturbed by this, but H was a related parameter because H is a square root of omega m over omega m. And in my parametrization, it was given by this combination. So in my basis of parameter, I can choose some omega or some H, or I could choose big or small omega. As long as you have a complete basis of 6 parameters, you will get all the effects. But you will mix them up. So I did a choice in which I believe that the effects were clearer on this graph. If you choose another parameter basis, on this graph, some of the effects will be a combination of these ones, and it will be more difficult to understand and less clear that the effects are all different from each other. It's only this. But to go a bit more, to give a bit of a better answer, so the big omegas tell you what is the density of one species relative to the total, and the small omega gives you the absolute density today. Because you can always write that small omega is a number with some units times rho x0. And what I was really interested was to vary the true density of baryons today or the true density of matter today, because these quantities play a role, especially this one plays a role compared to the true density of photons at recombination. And this one plays a role when you compare it to the total density of radiation. So this is why it's natural that you get a nicer discussion when you use the small omegas for the matter components. For lambda, you are not really interested in rho lambda 0. You are interested in the redshift of equality between matter and lambda. And this is something like omega lambda over 1 minus omega lambda with probably a cubic root. So taking a big omega was a good choice. Yeah. Sorry, can you say again? Yeah. 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 Yeah, it's accounted in your likelihood. So what is Gaussian indeed, we have seen is Gaussian are the ALs. The ALMs have a beautiful Gaussian distribution, at least when you measure them in an ideal world, full sky, etc. And the variance is a CL. But the CLs themselves are not Gaussian distributed because they come from a sum over the square of Gaussian. So they have a chi-square distribution with L degrees of freedom, which is like a distorted Gaussian. And of course, when you write a CMB likelihood, this is totally accounted for. There are different ways of writing this likelihood. It can be at the level of the ALM, at the level of the CL, or directly at the level of the pixelized maps. But in all cases, people are aware of this, and they never approximate the CL as Gaussian distributed. Yeah, actually, so at some point I transitioned from CMB to large-scale structure, and I was shocked to see that in many large-scale structure likelihoods, you treat these CLs as Gaussian. This is something a CMB physicist would never do. Yeah, yeah. Yeah. Yeah, can you just say again the beginning of the question? Ah, of the finite size, yes. Yes, the thickness of the last scattering shell and the silk damping are in principle, they are connected, of course. No, they are difficult to tell apart because the thickness of the last scattering sphere comes from the fact that the transition from zero mean free path to large mean free path is slow. And this is exactly what you get when you compute the diffusion scale. So I think your question is, when I expect that there was a smoothing, I said there is a smoothing along the line of sight, coming from the thickness of the last scattering shell. And there is an effect orthogonal to the line of sight, which is a smearing from the damping scale. And no, they are really connected because the physics of photon damping in the early universe is really symmetric in all three dimensions. So you cannot disentangle these effects. You cannot, I don't think you can think of a model where you would have more silk damping, but the same thickness of the last scattering surface. They really go together. Yeah. The relationship between the gravity boost and shifting of the redshift of the matter radiation. Yeah. Yeah. Let me go back to a plot where this is big enough. Yes. Okay. So you get a gravity boost. Where was it? Even before. Sorry. The gravity boost slide was here. Yeah. You get a gravity boost when you approach the Hubble crossing line during radiation domination. At the beginning of matter domination, there is still a bit of gravity boost, but then it fades away. So let me consider a mode that would be 10 to the minus 1. If equality takes place very early here, then the mode crosses the horizon during matter domination. And then phi will remain constant, meaning that this red region will extend to here. So the mode will remain always in a red region, will not see a big gradient of phi, and will not be enhanced by gravity boost. If this line is very low, then on the contrary, here it will be bluer. The mode, when crossing the Hubble radius, will experience a lot of gravity boost and will be enhanced. So there is a range of modes in the middle, which can be enhanced more or less by gravity boost, depending on the time of equality, given that the one of recombination is fixed. Yeah. Yeah. We would know that the reionization occurred even if we didn't have any CMB observation. We see it through when we would interpret the spectrum, for instance, of quasars at different redshifts. We would see that at some redshift, the universe was neutral. At some redshift, it was not. There is something called the Gunn-Peterson effect. So from astrophysical effects, you know that reionization took place. And actually, you get even more handle on this mechanism because with very good astrophysical observation or observation of 21 centimeter in the future, you could, in principle, reconstruct the whole reionization history, meaning you would reconstruct the free electron fraction XE of Z. And then you could connect it to your model for star formation. Depending on your model, on the fact that you have population 1, 2, 3 star appearing at different redshifts, you can make a prediction for what this ionization history should be, and then you can match this to astrophysical observation to see if your model is right. This is completely independent of the CMB. Nicely, the CMB gives you another handle, but not very detailed. The CMB gives you an information on tau rho, which is an integral over this ionization function. And then you can, in a way, confirm whether your CMB observation is consistent with your astrophysical observations or not. But the CMB is not sensitive to the details of reionization, only to its overall effect. Yeah. Yeah. Yeah, absolutely. Yeah. So this comes, so I go back to the last slide. You cannot have infinite curvature that would be compatible with a CMB observation. But when you allow for curvature, you have something called the geometrical degeneracy, which means that when you plot the contours for omega k versus another parameter, and you can put different things here, your contour seems completely degenerate. But this is usually because we are zooming on small regions. If you would have done these plots in an agnostic way 20 years ago, you would have taken a different scale, and this would have been an ellipse anyway. But the ellipse is very elongated, meaning that in your parameter space, if you have curvature, there is one direction where you can still do a measurement, but it's extremely imprecise. And the reason is effect C7, the late integrated Sachs-Wolf. This effect occurs in the region where the cosmic variance is the largest, so you can never measure it very well. So intuitively, you have a big axis here because your measurement error of the Sachs-Wolf plateau is big, and you have a narrow axis here because the other effects are much easier to constrain. So this is what people call the geometrical degeneracy, but still, it does not extend to infinity, because if you would have two extreme values, your CMB spectrum would have a very strong peak, a very strong tilting, and still, even if we have cosmic variance, we have measurements here. Yeah. Yeah.
Since all derivation, based on the integrated power factor,
Yeah.
since it occurred,
you need to define your modes in a different way. In a closed universe, the modes have discrete values. So what you need to do is a more complex expansion than a Fourier expansion. You need to expand over the eigenfunction of the Laplace operator in curved space. Then you get a lot of mass. The spherical Bessel function are replaced by hyperspherical Bessel function. It becomes quite complicated, but all this is in standard Boltzmann codes. Yeah.
okay, let us then.
Thank you.